First, interference is defined as when two or more waves interact with one another. Two or more waves interact with one another. And you've had common examples of interference, like if you're trying to tune into a certain radio station and a certain wave is overpowering the other wave that might be conflicting with it. Or if you think about interference, if you drop a pebble in a pond, it creates like ripples. But if you drop two pebbles in the pond, maybe 10 meters apart, you'll see their ripples kind of meet and they interfere with each other, usually coming together or canceling each other out. And we'll talk about that with superposition. So superposition is the fact that two pulse displacements can be added together when the two pulses exactly coincide or when they meet one another. So the example of that would be like the two ripples in the water meeting, and either they add up or they kind of counteract each other and subtract. And we'll see the differences in the next slide here. So first, constructive interference, a good example here, is if you have two waves coming toward one another, both with positive amplitude. So if two people were to flick the end of a rope or a slinky, and you saw two waves traveling toward each other, a big wave and a smaller wave, what would happen is they would start to form one wave together. And you kind of see the shape of the two original waves here, so they kind of come together, and then eventually they become this large wave here. And you'll see that the height of this wave plus the height of this wave equals the entire height. That is what superposition is. So if this wave had an amplitude of 2, say, meters, and this had an amplitude of 4, this would be an amplitude of 6. And then finally, after they come together, they pass through each other and come out the other side. So this big wave here that was going right is still going right, and it's over here. The small wave that was going left is still going left, but now it's over here, because they've passed through one another. Destructive interference is just simply the opposite. If you have a positive wave and a negative wave, they counteract each other, like a subtraction problem, if you want to think about it. They start to form one wave here. You'll see the beginning of that wave is still there, and the other wave is still here. But imagine that this wave is like a positive 5 meters, and this is a negative 2. Well, positive 5 and negative 2 is going to give us positive 3. That's what this resulting height would be. Again, if this were 5 and this were negative 2, this would be a positive 3. And it's on the up or the positive side of the rope because the positive wave was bigger than the negative wave. And then again, afterward, the two waves pass through each other. So this big wave that started going right is now going right still. The small wave that was going left is still going to the left afterward. Wave reflection is to take a look at whether the boundaries are free or fixed. And what we'll notice here is that when there's a free boundary, such as this example here, so imagine a rope is kind of looped around a pole where this loop is free to slide up and down. It's a free boundary. As you send a pulse on the top of a rope, the pulse is going to carry itself on the top, but it's going to cause the end of this rope to kick itself up. And then the rope is going to slide back down due to gravity. It's going to be pulled back down quick, and that's going to send a pulse backward. And that pulse is just going to be the reflected pulse of the incident pulse that you had sent. But if the boundary is fixed, then you can try this by just tying a rope to a fixed end. So if you were to tie a rope to, say, a handle on a cabinet, or a handle on like a drawer, or tie a rope to something where it won't slide up and down the pole. So tie the rope to this taut, or tie it so that it's fixed, so that this rope can't slide up and down. If you send a pulse, it's going to cause this rope to send the pulse backward to you, but on the other side, which means that the wave is not only reflected, but the wave is inverted. And you could try this. You could also just have two people. One person hold one end of the rope, another person hold the other end, and one person sends a wave. If the other person holds their end still, the wave that gets reflected will be also inverted, and you can see that. Finally, some examples of interference graphically, and this one I want you to notice right away, is that we have two initial waves that are resulting in a third and final wave. And it's not obvious that you can see this here, but all you need to do is draw a vertical line, and it's pretty obvious then. So I'm going to start by drawing myself a vertical line. And I'm going to draw this vertical line to make it easy right here to start. And what I'll notice is that if I label this, say this 2 and call this negative 2, so this would be like negative 1, this would be 1 here. If I notice this, the green wave has an amplitude of around 1. The blue wave has an amplitude of around negative 1, or like it's really more like negative 1.5, and this is more like positive 1.5. So I'm just going to label those, and this is the amplitude or the height of the wave. Again, I'm measuring the distance from here to here as the negative 1.5. This is the positive 1.5, the height. And what you'll notice is that when you add those amplitudes together, 1.5 and negative 1.5, you get 0. And that's exactly where the red node is. The red node is lined up with 0 over here. Okay, or the red point, sorry, the red wave. If I do this anywhere, it works. Let's take a look here now. All right, well, this is a height of about 1, right? So we'll say that this point is about 1 as a height. This is down here at around negative 2. Right, there's our negative 2. Well, what's negative 2 and 1 when added together? Well, 1 and negative 2 gives me negative 1, and take a look. The red wave is at a length or a height of negative 1. Negative 1. So whenever you add these two waves together, wave 1 and wave 2, you get the third wave. And you can check this by making continuous vertical lines everywhere. Now what I want you to notice is that the two examples I just gave you are both considered destructive interference, because we're taking a positive wave and a negative wave and seeing how they cancel, adding them together. Positive and negative canceling out with the third wave in between again. So when this resultant wave is in between the other two, so see how this is in between these two? It's destructive. But an example of constructive interference would be, what if I drew a vertical line, say, right here? Well, this would be a height of maybe like a third. This would be a height of 1. And then when you add a third and 1 together, you get 1 and a third. And notice that the third and final wave, or the resultant wave, is now outside of these two. So two positive waves adding up to a bigger positive wave. The same thing occurs with negative waves. If I drew a vertical line, let's say right here, I take a negative wave, or a negative amplitude, and another negative amplitude, and those add together to give me an even bigger negative amplitude from the red wave. So these two examples here would be constructive interference, because you have a positive positive making it more positive, a negative negative making it more negative. But here these are destructive because the original waves have opposite signs, so they're interfering with each other to make a wave that's in between. Again, same thing as far as this goes. This is a positive wave, this is a negative wave, making it neutral in this case because they're equal and opposite. But this would be destructive, again, for these two. And this one was constructive, overall negative though, and this one was constructive, overall negative as well.